in this problem, we want to evaluate the line integral over C, x plus y dx plus x times y dy. C is the boundary of the region lying between the graphs of x squared plus y squared equals 1 and x squared plus y squared equals 4. So we want to use Green's theorem to evaluate this thing. Yeah, directions use Green's theorem. We assume C is positively oriented. Okay. So the idea is don't evaluate this directly. Create a double integral that is the equivalent to this line integral based on Green's theorem. Okay, so in order to use Green's theorem, let's just write it down. It's always a good idea in these problems for you to write down these theorems. It'll help you memorize it. So the line integral, this is kind of the basic symbolic notation for the line integral with respect to the vector field over C. Integral over CF dot dr. So for a closed C, under the right conditions, it is true that this will be equal to the double integral over R of, anybody remember what it's dq dx, there you go, dp dy, dA. Some books use, so keep in mind if it's a closed curve, some books use that notation. Sometimes you'll see it, sometimes you don't, but if you see it, know C is a closed curve. That's what it means. So you look at that formula. The reason you write it down is you look at it and it tells you what to do. Now once you learn that, you got to memorize the formulas, and once you learn that, it's like memorizing a whole lot of other steps, because you look at the formula, you look at the innermost thing you need to find, it tells you what you need. So what's Q? So, Q is the guy attached to dy, right? And P is attached to the dx, right? So this, if you look inside this formula, it tells us to take dqx minus dpy. The partial derivative of q with respect to x minus partial derivative of p with respect to y. So let's do that first. That's our integrand. So I'll just write down what I'm doing, and I'll do it all in one step, or 2 steps at the most. So you guys tell me, what is dq dx, the derivative of x times y with respect to x, minus the derivative of p with respect to y, 1. So y minus 1 is going to be your integrand. That's not so bad, right? Now, we're essentially evaluating a double integral. It's back to the last chapter, right? So what would this region look like? Well, let's make a little graph over here. I'm pretty sure I know what both of these look like, right? X squared plus y squared equals 1 is the unit circle. I'll just draw it freehand. It won't look that good, but that's okay. So that's out a distance of 1, right? This is x, this is y. And then this is circle centered at 0, 0, radius 2. Oh, okay, so I can draw that. So go over here. Won't be a work of art, but that's okay. So, C is the boundary of the region lying between the graphs of x squared plus y squared equals 1 and x squared plus y squared equals 4. So we're talking about the donut, right? We're talking about the donut. And you might think, so the region R is in green there. You might think, oh, this region isn't well behaved enough for Green's theorem to apply, but remember the example in class? We could introduce 2 new segments to this if we had to, right? It's really, to do this problem, you don't have to do this, but if you introduce 2 segments two new lines in your line integral, one going that way. Now, I've drawn it so that it's above the x-axis, but it's actually on the x-axis. And it's parametrized kind of going inward. The other one parametrized, well, you know what, we could do it. It might be neater to make it go like that. And then the other one, which is also on the x-axis, we'll make that the one that goes inward. See if that makes any sense at all. So, actually it doesn't really matter. It would have been fine the other way. Either way, these are both line segments on the x-axis. You could call this top one C3, this bottom one C4. And then remember, the idea is integrating the line integral over C. Oh, that's the union of what? C1, C2, and now we're introducing C3 and C4. And the idea is that the line integral is going to be additive, right? Now this is the notation that only instructors get to use. But this integral will equal the integral over C1 plus the integral over C2 plus the integral over C3 plus the integral over C4. But what about C3 and C4? C3, notationally, we could write C4 or C3. One is the opposite of the other, right? Meaning that it's the opposite orientation, right? And so if you think of C4 as the opposite of C3, you could replace the C4 with that notation, which is equivalent to subtracting off the integral over C3. They cancel, and the original line integral over C is going to equal the sum of those two integrals. Now, why do we bother with all that? Well, you have to remember, to understand why we bother with all that, is you have to remember the hypothesis of Green's theorem. Basically, you have to be able to trace out the curve C in order for Green's theorem to apply. You have to be able to trace out the curve C without lifting your pen or pencil in a counterclockwise fashion. Well, okay, what do we mean by that? Forget counterclockwise, think positive fashion, so that the region is always on your left if you're an ant traveling along the curve, right? So okay, let's trace this out and see if it works. We'll use a big old highlighter, big old yellow highlighter. Okay, so you can start anywhere you want, right? On C, it doesn't give us a beginning point and an end point. So you would want to start in a counterclockwise fashion, right? To keep the area, now you're the ant traveling that way, so you want to keep the area on your left. And then maybe I should have chose blue. Okay, start over. So you're an ant traveling along this curve. You're keeping the region on your left. That means you're going in the positive direction. And then, you travel along the x-axis via C4. And then, which way do you have to travel inside? So this part of the curve is oriented that way. To keep everything on your left, you'd actually have to go clockwise inside, wouldn't you? That's okay. That's why it's really confusing when you say you're moving counterclockwise. It's not always true, in other words. Whoops, let me get on the right thing here. Okay, so you're in here, traveling along. Then you go, and the region will be on your left when you travel along inside like this. And then you go back out via C3 on the x-axis, and then you keep traveling along here to close it out. So that's the requirement. That's why we mess with all that. Now, in the homework, the first question that's going to pop up is, do we need to show all this? No, I suppose not. Just let's go right to evaluating the double integral, right? But it's important to understand why it works. And I can hold you responsible for that part of the problem in another context, like make it a separate problem, right? So understand the argument, okay? But as far as this particular homework problem goes, if you didn't show all that, I'm okay with that. okay, then our line integral becomes the integral f dot dr equals, okay, the double integral, we'll just say over r, the region r. Our integrand we know is y minus 1, and then we have what, dA? Now, why did I not want to write it out? What am I going to switch to right away? Polar coordinates, right? So you would want to show a picture of r for that setup. And so if we switch y to polar, what do we get? R sine theta minus 1. Then your dA, your area element, r d theta. And then what, okay, now put in your spoke. Now, the part of the spoke down here near the origin, we'll make it dotted because it's not actually part of your region, right? And then this part is solid. It goes from here, the minimum distance, radial distance is here, maximum radial distance is there. So what does r run from? 1 to 2. And then, let's see, theta is going to go all the way around, 0 to 2 pi. Is there a good way to split up that integral? I think you could make an argument since the limits of integration are constant and, oh, darn it. You're right. Nope. My eyes went to the fact that the limits of integration are constant, but there's a darn theta in there. We can't split it up as a product of two integrals, right? But it's always a good thought to think about because it makes it look a little easier when you can do it. All right, so let's just integrate it the old-fashioned way. Brute force. Okay, integrate with respect to r now, the inner integral. We'll leave this guy here, 0 to 2 pi. With respect to r, what do you get? Oh, you know what? Let me distribute that r first. So let me do it within this here. So what do we get when we distribute that r? R squared sine theta minus r. What do you get? 1/3 r cubed sine, I'm having trouble, sine theta minus 1/2 r squared. And then dr d theta. I'm sorry, just d theta, no dr. Oh, we have to evaluate that, don't we? From what to what? 1 to 2. So let's do that. So leave this symbolism here. And what do we get for this first guy when we plug in 2? So 8/3 sine theta. Minus 2, right? That's just when we plug in the upper limit. And then when we plug in 1, so minus, what do we get when we plug in just 1 for r? 1/3 sine theta minus 1/2. And then we still have the d theta. Everybody with me? We do have like terms, don't we? So I recommend, distributing that minus, getting the signs together, getting the constants together and making your life easier before you try to integrate. So integral 0 to 2 pi. Okay, if we distribute this, it actually becomes what? Minus 1/3 sine theta plus 1/2 here. So let's add those together. Let's add the minus 1/3 sine theta to the 8/3. What do we get? 7/3 sine theta. And we have a minus 2 plus 1/2 minus 3/2. And then d theta. Okay, everybody in agreement? All right. So let's integrate. What do we get? So we integrate sine theta, and it's actually negative cosine, and we'll keep that 7/3 out front, but make it negative. And then minus 3/2 theta, and you evaluate from 0 to 2 pi. Okay, what do we get when we plug in 2 pi for cosine? All right, so just negative 7/3 out times 1. And then when we plug in 2 pi for theta here, we get minus 3 pi. Do we get anything when we plug in 0? We do. So that's just the first bit when you plug in 2 pi. And then when you plug in 0, yeah, of course this guy in the back end zeroes out, but this guy, cosine 0 is 1, so we get, well, minus from the fundamental theorem, but then negative 7/3, right? Everybody buy that? So what do we get there? Just negative 3 pi. It's kind of interesting.